This lesson describes the arithmetic data types of Java. Java has 9 fundamental data types. Of these, 7 are numeric and can be used for arithmetic. These are the data types that are built into the Java virtual machine and have arithmetic operations defined for them as part of the Java language. The fundamental data types are the building blocks from which all complex data is constructed. The smallest of the arithmetic data types is the byte. It's an 8-bit integer value. It can contain a maximum positive value of 128. Next is the short data type, which is twice the size of a byte and takes up 16 bits. Just like the byte, it's a signed data type, which means it can contain both positive and negative values, and it can contain a maximum value of 32,767. The next data type is the char, or sometimes pronounced char. It's the same size as the short, but it's an unsigned value, with its largest value being 65,535. In fact, this is the only unsigned value in Java, and while you can do arithmetic on it and convert its numeric values to and from the other fundamental data types, it's intended to hold members of the character set of Java. The character set of Java is Unicode. This means that Java character data can be composed of any characters from any alphabet in the world. Every character in every alphabet has a numeric value assigned to it, and that value will fit in a Java char data type. The ASCII character set has its set of numeric values, which range from 0 to 127. To be compatible, the first 127 values of the Unicode character set are the same as the values of the ASCII character set. So, Java can work with ASCII data without any conversion other than from 8-bit character values to 16-bit character values. This size change only comes into play when Java is doing file input or output, so it can usually be ignored altogether. We'll be getting into it later with reading and writing files, but even then it's mostly automated and not much of a bother. Here we have our star. If you had to pick one data type that was more popular than all the others, it would be the int. It seems to be the one that's used most often. It's normally the one we choose for indexes and loop counters for simple arithmetic and to generally keep track of numbers for us. It's a signed 32-bit value. Most computers today are 32-bit machines, so we tend to use 32-bit values without thinking much about it. One really nice thing about a 32-bit integer value is it holds a range large enough to perform most arithmetic operations without running over. Its largest value is 2,147,483,647. The largest of the integer values is the long data type. By the way, the sizes of these fundamental data types don't vary from one machine to the next the way they do in C and C++. In Java, all the data type sizes are fixed. The long data type is a signed integer that takes up 64 bits. This means that the long data type can hold a maximum positive value of 9,223,372,336,854,775,807. This is the data type that's used to contain date and time information. In Java, timestamps are in the form of a count of the number of milliseconds, both positive and negative, from January 1st, 1970, and the span that can be represented goes 250,000 years into the past and into the future. And that's it for the 5 fundamental integer types of Java. In addition to the integer types, Java has 2 real number types. A real number is any number with a decimal point. The first real number data type is called float. It's the smaller of the two and takes up 32 bits of space. This makes it the same size as the int. The 23-bit mantissa provides something just over 6 digits of accuracy, and the exponent can specify large numbers with the decimal point as far as 38 positions to the right and as small as 45 positions to the left. The 32nd bit is the sign bit. The larger floating point format is called double. That's because it's twice the size of a float. It takes the same size in memory as the long does for an integer. The 52-bit mantissa provides an accuracy something just over 16 digits, and the 11-bit exponent can be used to express either a positive exponent as large as 308 or a negative exponent as small as minus 324. The 64th bit is the sign bit. By the way, both the float and the double data types use the IEEE 754 1985 standard format. That's it for the 7 arithmetic types of Java. 5 integer types, 2 real types. With only one exception, every time you see addition, subtraction, multiplication, or division in Java, one or more of the items in this list are involved. That one exception has to do with addition only, and we'll be covering that one shortly. This lesson explains the 2 remaining fundamental data types and explains some of the relationships among the various data types. Java has a non-arithmetic data type. It can only take on one of 2 values. It's the Boolean data type and is always set to either true or false. Now, the names true and false are both keywords in the language. They're the only things that you can assign to a Boolean data type. You can't use numeric values of 1 or 0 for logical operations like you can in C. Conceptually, the Boolean data type is 1 bit wide, but that doesn't matter because you can't use it in arithmetic anyway. There is one last data type. You can actually argue that it's not one of the data types of Java. All it can do is hold the address of an object. You can't even set its value to an object of the incorrect type. All you can do is set its value to null or to the address of an appropriate type of object, and then use it to refer to that object. Whenever you declare a data item, whether it's inside or outside of a method, and you don't specify an initial value for it, Java initializes it for you. All of the numeric data types are initialized to 0. This is true for both integers and real numbers. The Boolean data types are initialized to false. Unless you specify the address of an object to be stored in them, all references are initially set to null. Null is another keyword of the Java language. For the arithmetic types, you can convert data from one type to another by simply assigning the data from one to the other. If the 2 types are not the same, you'll either be widening or narrowing the data. If you're widening the data, you're making it larger. If there is more than enough room in the receiving field to hold all possible values of the originating field, then you're said to be widening the data. There's no possible loss of data, so Java allows you to do this directly. For example, copying a short value into an int, you will never lose any data because an int can contain everything that can fit into a short. On the other hand, if you're reducing the size of the data, you are narrowing the data and could trim the value when it's copied into the new location. For example, copying an int value into a short value could trim the actual data if the value stored in the int was too large to fit into the short. For example, copying an int value into a short value would trim the actual data if the value stored in the int was too large to fit into a short. When you do this, the Java compiler will require that you cast the assignment to indicate that you realize you are narrowing the data and may cause some sort of inaccuracy. For example, here we have a short and an int. Notice that the value from the short to the int can be copied without any special notation, but the copy from the int into the short requires that you precede the source of the data with a cast, which means that you are forcing the data to be a smaller size. Oh, by the way, if you're not sure, you don't have to worry about using a cast. If you don't use a cast and you write a line of code that's narrowing the data, the Java compiler will flag the line for you, and you can either add the cast so the compiler will know that you meant to do it, or you can change the code so no loss of data is possible. The purpose of any computer program is to manipulate data. This lesson contains a description of the arithmetic and assignment operators of Java. The form of some of the special operators were derived from C, but even if you're familiar with C, you should stay tuned because you're going to find a surprise in here. Now, this class doesn't actually do anything to produce a result. It was devised just to show you the array of arithmetic operators available in Java. All the operations in this class operate on the int values A, B, and C. Here, they're all three declared and assigned initial values. The values don't mean much in this application, but they do keep the compiler from complaining. This is probably the most common operation of all. This is the assignment operator. It causes the value to be calculated from the expression on the right and stored in the location specified on the left. This is the form that exists in almost every programming language. The operators of add, subtract, multiply, and divide can be used between any two values of any numeric type, and the result is calculated and assigned to the variable named on the left. In these examples, the data items are the same size, so there's no need to cast anything to narrow the result to make it fit. Now we come to a bit of a special situation. This is something that happens a lot. In this expression, the value of A is being modified by having the value of B added to it. In Java, this can be written in a shorter form by using the special assignment operator that adds to the value on the left instead of simply replacing it with the value of an expression. This non-traditional form of combining arithmetic and assignment into one operator was introduced in C. If you're a programmer and this is new to you, it'll take a bit of getting used to. Actually, it didn't come about because of it being some kind of convenient shorthand. It really came about because the computer on which the first C compiler was written had hardware instructions that would do this. There was no automatic optimization in those days, so it was more efficient to write code this way. Today it doesn't matter. You can write the code any way you like, and the compiler will mush it around to fit the target machine. In Java, of course, the target machine is the Java virtual machine. Now, this form of the operator doesn't exist just for addition. There are also versions of it for subtraction, multiplication, and division. And there is one other binary arithmetic operator, the modulo operator. The percent sign performs the same operation as the division does, except the result is taken to be the remainder. It isn't used as often as the other four, but it can come in very handy in special circumstances. We'll be using it later when we get into animation. And just like the other four operators, this one also can be written in the combined form. These two statements are identical as far as Java is concerned. These are the bit shift operators. The first one will shift the value of A 3 bits to the left, thus doubling the value stored in A 3 times. The second shifts the value of A 3 bits to the right, thus halving the value 3 times. Now, with this right shift operator, a negative number will remain negative by having its sign bit replicated on the left. This last one is also a right shift operator, but the sign bit will not be extended, causing a negative value to become positive. The shift operators can also be written in the combined form. In fact, with the shift operators, this is probably the more common form. The last of the binary operators are the bitwise operators. Now, these only work on integer values. The ampersand is the bitwise AND of two integer values. The vertical bar is the bitwise OR of two integer values. And the caret is the exclusive OR of two integer values. Now, these bitwise operators are not really used that often, but special circumstances arise where you do need them. There are a couple of special operators in Java that are used to add one or subtract one from a variable. These are called the increment and decrement operators. Now, this block of code sets the value of A to 5, prints it, then prints it again as it is being incremented, then prints it a third time to show the final result. Now, this is called a post-increment because the increment does not occur until after its value has been used in the statement. That is, placing the plus plus after the A means that after everything else in this statement has been completed and calculated, 1 is added to A. Now this is the pre-increment form of A. This works the same as the post-increment form, except one is added to A before anything else is done in the expression. Now the decrement operators are written as a minus minus and can be used as either a post-decrement or as a pre-decrement, except it subtracts one instead of adding one. In this example, the value of A is set to 5. Then the values are printed that demonstrate how the increment and decrement operators work. Here you can see the result of a post-increment, which doesn't show up until after the statement on which it occurred has finished, where the pre-increment shows up before it's been used in the expression. The same is true of the pre- and post-decrements. If these operations are new to you, I suggest you examine the example program and compare it to the results. These operators are used a lot in Java, as well as in C and C++ for that matter. Well, that's about it for operators. In an upcoming lesson, we'll be looking at the Boolean operators, which are used to compare values of two numbers, but it's easier to explain those in terms of if and while. But this lesson contains everything you need to do arithmetic in Java. This lesson explains the very special string class of Java. It's not one of the fundamental data types, but it is a very special type. The string class is actually a part of the Java language because the compiler knows how to use it to generate special code for it. This is the main window of an application. It has the same form that we've been using in some of the previous lessons. It extends a frame class and then creates a string demo object and adds it to the window for display. This is the string demo class, which extends the canvas object. It demonstrates some of the different ways of creating string objects. As you'll soon see, anything in Java can be automatically converted into a string object. At the very top of the paint method, we call getBounds to get a rectangle object containing the bounds of the window being displayed. We also call the getFontMetrics object to get the size information of the current font. We're going to display several different strings in the window, so X and Y are initialized to the position of the first string to be displayed. Now here we have the declaration of a reference to a string object. Remember, because we have not stored anything into the references yet, its value is still null and no string object as yet exists. Now this line of code creates a string object containing the quoted characters and stores the address of the object in the reference. This statement is, in fact, identical to the function statement that follows it, where the string is explicitly named and a new statement is used to create the object. The compiler does this. Whenever the compiler sees a quoted string of characters anywhere in your program, it inserts a new string statement to create the object. And this statement is exactly the same as the ones above it. It's just written in a different way. You never have to write new string because the compiler will always do it for you when it finds a quoted string of characters in your code. This call to draw string draws the first string in the first position of the window. The window produced by the program looks like this. This top line is the one that's displayed by the first call to draw string. Notice the use of the addition operator in this next line. It's used here to create a new string object by combining the contents of string 1 with string 2. Whenever the compiler finds a plus sign with an item to its left or right being a string object, it knows that it's combining two strings and it creates a new string object to hold them. This call to draw a string produces this line of text, which is a combination of the first of the two strings. Now, notice how the position of the second line of text is determined. If you recall, the height of a font not only includes the height of the visible text, but it also includes the height of the leading, the space between the lines. So it's only necessary to add the height to the current position to determine the position of the next line. The next string is constructed by using the plus equals operator to add the next string to the one we already have. Now, you should be aware that although this statement looks like it's combining a new string with the one that already exists, that's not actually the case. The string objects are immutable. That means that once they're created, they can't be modified. This statement actually is creating a new string object that replaces the existing one. The operational difference is moot in this particular case, but other circumstances will arise where the difference is important. Anyway, the resulting string is displayed here, and it contains all three of our original strings. Here we declare ourselves an integer value that we want to display. The integer value is converted to a string here by simply being added to another string object. Here's the deal. Whenever you add two things together and one of the things being added is a string, the other one is automatically converted to a string, and the two strings are then combined to form a new string. The output looks like this. You can add several strings together at once, and the conversion thing still holds true. Here are several plus signs between values and strings, one of the value being an integer, the other one being a float. The result is a string with both an integer and a float. You can add as many values and objects as you wish to a string, and it will always produce a new string with everything you've added to it converted to a string if necessary. Now, in these statements, three separate objects have been converted to strings by being added to existing strings. As you can see, each object, a color, a rectangle, and a font metrics object, have all been converted. Each one displays in its own way. A color uses its three internal values, a rectangle uses its four internal values, and a font metrics object displays all of the font metrics information. You'll find that other objects produce simple strings that include only their names or even just a text version of the address of the object, but the point is that everything in Java can be converted directly to a string. This lesson is an introductory explanation to the declaration of arrays. Like just about everything else in Java, they're objects, but they're special objects, and you declare them in a special way. This is the declaration of a reference to an array. It's not an array, it's a location in memory where we will be able to put an array. This statement creates an actual array of integers and stores its address in the reference declared earlier. We now have an array. This is an array of 10 integers, all initialized to 0. An array of objects is declared the same way. First, we declare a reference to an array of the objects, and then a declaration is made of an array of object references. We still don't have any rectangles. What we have after this statement is the stored address of an array of rectangle references. All the references are initialized to null. These three statements create the actual rectangle objects and store them in the array of references. Note that array subscripts always begin with 0. This is because Java subscripts are thought of as offset values, and the offset from the beginning of an array to the first member of the array is always 0. So we declare an array of size 3, but the largest index value is 2. More about this later. This statement declares an array of double data items and provides them with initial values. Notice that the brackets are on the type declaration rather than the name as was done earlier. You can put them in either place. Java doesn't care. But this array declaration has a set of initial values provided for it. This instructs the compiler to create an actual array of doubles and store the values for them in the array. It's just a shorthand for writing all the individual statements. The size of the array is determined by the number of initial values included in the braces. Arrays are always a fixed size. Once you've created one, you can't change its size. The only way to change the size of an array is to create a new array and replace the old one. Every array object has a length attribute that you can use to determine the number of members it contains. Here we copy the value of the length of Harv into a new variable named length of array. A call is then made to systemoutPrintln, which displays the text form of anything provided to it. This method takes advantage of the fact that everything in Java can be converted to a string. In this example, the number 4 is displayed because that is the number of members of the array. Multidimensional arrays are declared by having more than one set of brackets on the declaration. This example is a two-dimensional array. You can declare an actual array by using the new keyword and providing the actual sizes you want. In this case, this code declares a 5 by 10 grid of 50 integers, all initialized to 0. That's a look at the fundamentals of arrays. In Java, you must declare a reference to hold the address of the array, then create the actual array and store the address there. We'll be doing more with arrays in the near future. This lesson introduces the Java if statement and the form of conditional expressions. The flow of execution of the statements in a method is from top to bottom, but you can specify that certain statements in the method be executed only under certain conditions. In this example, this if statement is used to determine whether the value of A is less than B. Now, in this simple program, the conditional expression will always result in the Boolean value of true, and the statement following it will always be executed. This if statement is a test for the value of A being greater than B, and if it is, the statement following it will be executed. And in this example, the statement following is a compound statement of two expressions. A collection of two or more statements like this can be treated as if they were a single statement by being enclosed in braces. Java is a free-form language. That is, you can put several spaces and tabs and even a new line wherever a single space would work. Java doesn't care where you put things as long as it can tell where one thing ends and another one begins. Everything between them is ignored. As we go along, you'll notice that I have a certain way of placing braces and indenting code. This is my personal style. Mostly it's pretty common style of code that I've carefully copied from programs that I've read and liked over the years. As you become more familiar with Java, you'll notice two things. First, every programmer has some style preferences of their own. Second, the style that someone uses doesn't matter much as long as they're consistent. Reading someone else's code is relatively easy to do as long as they don't throw you too many surprises in the format. Lots of people are bothered by the placement of the braces, whether they should go on the same line as the code or on a line of their own, and whether and how they should be indented. Java doesn't care. The reason I use the style that I do is so I can pack as many lines of code on the screen as possible and still have it readable. You should pick a style of your own and be consistent. Anyway, I was talking about Boolean expressions. There are a number of operators that can be used to compare one value to another. Each one of these results in a Boolean value of either true or false. The double equal sign results in true only if the number to its left is exactly the same value as the number to its right. To test for the two numbers not being equal to one another, use the exclamation point and the equal sign. The rest of the comparison operators look pretty much the same as they do in any programming language. The test is for the number on the left being less than the one on the right, or being greater than, less than or equal to, or greater than or equal to. You'll almost always find one of these in an if statement, or as the test expression in a loop to determine when the looping is done. There's an interesting thing about Boolean operators. Some programmers like to use them in combinations and others don't. It's apparently a matter of programming style, but some people seem to use the Boolean binary operators and or quite a bit, while other people almost never use them. The double ampersand is used for ANDing. It's only true if the Boolean expression on each side of it is true. In this example, the expression is true only if A is less than B and C is equal to D. If either comparison operator is false, then the whole thing is false. The double vertical bar is the OR operator, and will result in true if either of the two Boolean expressions on the sides of it are true. The vertical bar is a standard ASCII character and is found on every keyboard. You'll normally find it on the same key as the backslash. Sometimes it's broken in the middle and looks sort of like a colon that's been stretched out. This expression is true if either A is less than B or if C is equal to D. Many people, when they first start working with Java, want to use the Boolean operators to compare things like strings. It won't work. The Boolean operators are strictly for comparing numbers. It's possible to compare the contents of objects, but to do so requires that the class of the object provide a method for doing just that. Just remember that the Boolean operators are only good for numbers. This lesson takes a look at the Java keywords for looping. Looping is simply executing the same block of code repeatedly until some condition is met. Every loop is made up of four things. Initial values are set, a condition is checked to see if the looping is done, an adjustment of some sort is made before the loop starts over from the top, and every loop has a body of executable statements that are to be repeated once for each loop. Java has three different forms of loops. The while loop has its test at the top of the loop. That is, a Boolean expression is evaluated, and if that expression results in true, the body of the loop then is executed once. Once the body has finished executing, the same test is made again. The loop will continue to execute over and over again as long as the expression remains true. In this example, the index value was preset to 0 before the loop began. As long as the value of the index is less than the count of the number of arguments in the arg array, the body of the loop is executed. Inside the loop body, the command line argument at the current index is displayed, and the index value is bumped up by 1. Notice how the value of index is tested. It begins at 0, which is the index to the first member of the arg array, and the loop will continue to execute as long as index is less than the number of members in the array. That means, for example, if there are 5 members of the array, the maximum index value in the loop will be at 4, which is correct. The maximum valid index for an array is 1 less than the number of members of the array. The do-while statement is very similar to the while statement, except the test is made at the bottom of the loop instead of the top. This means that the do-while loop will always be executed at least once, even if the Boolean expression would evaluate to false. That means that this program has a bug. The body of this loop will attempt to display one command line argument even when there are none. Notice how the index value uses the pre-increment. 1 is added to the index value before it is tested against the number of members of the array. The for loop is the most common form of looping in Java. As you can see, the for statement itself is divided into 3 parts, separated by semicolons. The first part is used to set any initial values. It's normally a single counter like this, but you can actually put several statements here by separating them with commas. This is the test to determine whether to loop. The test is always made at the top of the loop, so it's possible if the first time through the Boolean expression results in false, the body of a for statement will never execute. Here's the third part, which is the adjustment to be made before the next loop begins. In a for loop, this adjustment statement is always executed at the bottom of the loop, just before coming back to the top to perform the test again. You can actually put as many adjustment statements as you like in here by separating them with commas. This is the body of the loop. In this case, it's a single statement, so it doesn't strictly have to be enclosed in braces here and here. But I have found that by always putting braces around the bodies of for loops, the code is easier to read. It's up to you. As you can see, each loop in this program prints all of the command line entries. Generally speaking, the command line entries are separated by spaces. This is actually a part of Java that's not entirely portable because each operating system analyzes and modifies the command line entries in a different way. As far as Java is concerned, the entries on the command line are separated by spaces. But some operating systems process wildcards and such to make modifications to the command line before Java ever sees it. Remember, I said that this program had a bug? Let me show you what happens when this program is run without any command line arguments. Here, the do loop tried to execute once and access the first member of the array. Because there are no command line arguments, the array had no members, so the subscript value was beyond the range of the array. An error message was printed and the program was halted. Java was also able to print the exact line number in the source code on which the error occurred. This is a very handy piece of information when you put some sort of surprise for yourself in one of your programs. This lesson shows you how to write a simple program that lists the names of the fonts available on your system. You can use any font name you find in this list, but that doesn't mean that the font is installed on all computers that have Java installed. So if you write a program that uses a particular font, that same program may have to resort to the default font on another system. A class by the name of GraphicsEnvironment has a method named getLocalGraphicsEnvironment. Now this method is static, just like the main method is static in classes that can be executed by the Java virtual machine. That is, the method exists in the class file and can be called directly without first having to create an object of the class. This method returns a graphics environment object that contains information about the local graphics environment. You don't have to bother with the graphics environment class very often, but we want to get a list of the fonts, so we need to go here because that's where they're stored. A call to the getAvailableFontFamilyNames method returns an array of string objects, and each member of the array contains the name of one font family. Note that at the beginning of this method, we declared a reference to an array of string references. Now the actual string array is constructed inside this method, and a string object containing the name of a font family is stored in each reference of the array. Then the address of the entire array of references is returned and stored in the local array reference. This for statement loops through all the members of the array and prints each one. There's something new here in the way the loop counter is declared. This is a bit of a special syntax just for the loop. Notice that the index named I is actually declared inside the parentheses of the for statement. Also notice that the value of the counter is used as an index inside the loop. The thing that's special about this is the scope of the variable I. Normally, you declare a variable between a pair of braces to make the variable exist only within those braces. The for loop is a special exception. The variable I is declared in the parentheses of the for, but outside the braces of the for body. So it exists inside the parentheses, but it also exists inside the braces of the body of the for loop. But it does not exist anywhere else in the method. You can't use the value of I anywhere except in the parentheses and inside the for loop. This is a special case in the scoping of variables, and we're going to be getting into more of that a little bit later. There you have it. If you want to use this list to select fonts, you probably want to redirect the output into a file, which you can do like this. Or you may want to pipe the output through more, which you can do on Windows or on any Unix system. This way you can press the return key to look at one more font name, or press the space bar to get an entire new page.